Alrighty, here we go. So, welcome folks to the MATLS 203 review session. So I'm Sarah. I use she, her pronouns. I'm in my 5th year of materials and bio out of 6 because all the cool kids take 6 years to do their undergrads. So a few disclaimers before we start. So first of all, I am a student. I'm not a professor or a TA, so I actually I can't guarantee that everything I say is going to be totally correct. I also don't actually have solutions to the test I'm going to be working through. I'm going to be working through the exam that I wrote back when it was online, which is why I have a copy of it. And I have my grades, so I know what questions I got right, what questions I got wrong. But I can't actually tell you that everything is going to be technically correct and exactly as the professor wanted it, because I'll just be going through what I did. Another disclaimer is that as mentioned, I'm a student, which means that I also have exams and projects and things like that. So I have not reviewed for this as much as I normally do for my review session. So I will be trying my very darn best, and that's about as much as I can promise you. And then a couple quick things to go over. So I'll just get a new window up. So a couple things that can be of use to you. So if you go to bit.ly/msc-course, then this will take you to our course resource page if you haven't seen it beforehand. So we're going to be looking at 2B03. Some resources here for you if we go to exam. So I'm going to be working through the 2021 exam student solution. So if you open this up, this is actually the exact thing that I'm going to be working through, just kind of telling you my thought process. Yeah, this is the one where I got 0 to 10 on it, and we're going to have Keith explain it for me because I genuinely don't know how to do that question. We're going to be working through that. If you want a blank copy, you can go to 2021 final exam blank. And you can find it here. So that's what I'll be working through and explaining it. You can also find some other exams as well as, I think for 2020, we didn't have, no, these were student solutions by another student. So we don't know the mark that they got. So just take that into consideration. Another resource for you, if you go to bit.ly/msc-YouTube, you can find our Material Science and Engineering Society YouTube page. Fun fact, this is back when I had long hair. Haha. But these are all the review sessions that I did back when I was in 2nd year. So you can find review sessions most specifically right now for 2P04 exam review session and the exam review session back then. So that would have been going through, I think, the 2020 exam back then, and then whatever we did for 2P04. I think it was more of a Q&A session. So if you're looking for more resources or for any of your courses, this is also a resource available for you. One of my friends always mocks me because she's like, Sarah, you had long hair. And I'm like, shut up, I know. I like short hair a lot better, but these are available for you, and just want to make sure that, yeah, you're cognizant of that. So we also have, yeah, I'll just leave it at that. You can peruse as you will. With that, we're gonna get started. So for folks who are online, I can't see you. So if you have any questions, oh, I should unmute myself. If you do have any comments, feel free to just unmute yourself and say it. I have now unmuted my speaker, so I'll be able to see it or I'll be able to hear it when you do that. And for folks in person, just ask me questions. Also, for everyone who's online, you're missing out because I brought snacks. So we're all going to be munching on our snacks. I did mention that on my Instagram, so you should all just pay attention to when I post stories about this, reminder stories, because I'll tell you when I have snacks. Anyways, all of that is said and done. Oh, the other disclaimer is that I wrote this back in the middle of COVID, so our exam was actually open book online. So your strategy might be slightly different than what I did, but to prep for this, so folks in person can see it, to prep for this, then I made my little formula sheets that had all of the general concepts on them. I think it's a really good study strategy, even if you can't actually take it into your exam with you, because you guys actually have in-person components. Anyways, we're gonna get started. So you open up the exam and it's like, okay, we have 10 questions. We had 135 minutes plus 15 minutes to scan and submit it, so ultimately about 2.5 hours. Some important things to note is that we needed to include units on all questions. We want to show our work as much as possible to get partial marks. Imagine getting 0 to 10 on a question. Gosh, even when you're showing your work. I'm mocking myself for getting 0 to 10 on that one question. But then, yeah, essentially you just need to show your work as you do it. Yeah, and those are the key non-online school things. So the first is a multiple choice question. So here we're talking about a reaction A plus B is equal to 2C. And we're given this little diagram of what's going on. And we want to see which is not correct. So the first thing that we want to do is we want to kind of understand the graph that we're looking at and what we're kind of looking and what all of the different symbols mean. So we're looking at a Gibbs free energy graph of the reaction. And there's many different components here. So we have delta GR, that's the Gibbs energy of the reaction. So as we undergo this reaction, we're going to decrease the Gibbs free energy because it's a spontaneous reaction, so it's quite happy doing so. And that's going to be decreasing over time at a very constant rate because it's proportional to the number of moles of C that have been created. We also have, I'm going to use a fancy laser pointer. We also have delta GM, and this relates to the Gibbs energy of mixing. So this is dependent on the amount of, moles of A versus B versus C we have present. So basically how mixed up the solution is, which is why we start out at some value because we have a mixture of A and B. So we're mixing and we're enjoying that. And it peaks somewhere, kind of near the middle where we have a mixture of A and B and C, and they're all mixing up together. But then at the end, it goes down to 0 because at the end, all we have is 2 moles of C. We have no A, no B left. So it's homogeneous. So we no longer have any Gibbs free energy of mixing left. The overall Gibbs free energy of the reaction is the combination of both of these processes that are going on, which is why we're given the overall in red. And it has a little curve shape. So now we can start to go through and answer this question. So the first one is delta G is equal to delta GM plus delta GR. We just said that that's true because that's kind of the definition of the total Gibbs free energy of the reaction. The next is that delta G naught is equal to negative 5,000 joules. And so for this one, we have to understand what is delta G naught. And this, oh, high key, I'm just going to make sure that I'm not totally going to tell you guys the wrong thing. Yeah, okay, so this relates to, there's a few different ways you can approach this. The first is to be like, okay, what does delta G naught mean? And is that at the correct value? Or we can look at it from another way. If you're like me right now and you're like, man, high key, it's been a long day. I don't exactly remember what that is. I don't want to give a definition for what delta G naught is. We can look at the graph and be like, okay, what is negative 5,000 joules? Where does that correlate to? So if we go to negative 5,000 joules, we see that it intersects, at a few different spots, but a very likely spot is right at the end. We have this value. And you can see that this is right at the end of the reaction, when we have 2 moles of C, and that this is the delta G of the reaction and delta G of the whole thing. So clearly what this delta G naught means is that this is the overall delta G of the reaction when it goes to completion, right? It's better to just know that, but if you're like me and you haven't studied or prepped for this, then that's kind of a good way to kind of work backwards from here. And we see that it is in fact at negative 5,000 joules, so that's true. The next question is, or the next statement is that equilibrium occurs at a composition range of this. So the way that we're going to look at this is we're going to find that composition range somewhere between here and here. And now we need to figure out what it means by equilibrium. So you think for a reaction that it would go to completion, right? We start at 1 mole A, 1 mole B, we end with 2 moles C, but that's not necessarily the case. Because they reach this little happy medium where they have a balance between, oh, we want to decrease the Gibbs free energy by mixing it or like by undergoing this reaction, doing the bond enthalpies and, forming the nice bonds. But we also want to have that Gibbs free energy that comes from the entropy of mixing all of the different like components together, right? If we have a big variety of things in there, that's lots of entropy. So that means that, we like that, we're happy. Because entropy always wants to increase. So we want to have some balance between that. And we can look at that by looking at the overall delta G graph. And ultimately, the big theme behind Gibbs free energy and what you always have to remember is that we want to be at minimum Gibbs free energy. We want to decrease it as much as possible. So we're going to be at equilibrium when we're at the minimum Gibbs energy, delta G overall. And that does occur somewhere in this range. Where exactly, hard to tell. But we know that this is then true. So you can say that, therefore, that, this has to be false. But if we can actually look at it, the reason that this isn't true, so this is saying that delta G of the reaction is equal to the number of moles of C times the overall delta G, like delta G naught, so like the overall delta G of the complete reaction. And in some cases, this is true because if you have, let's draw it here. If you're just making 1 mole of something like A plus B is equal to C, you'll end up with something like this. Terrible, terrible, whatever. And it's a linear line, right? So you can say that, yeah, we're equal to, some slope, whatever, and you can work it out to say that delta G reaction is equal to NC times delta G naught. But in this case, remember, we're making 2 moles of C, not just 1 mole. So if this were true, if we multiplied, let's just take an example. Let's say NC is equal to 2. Now, if we were to plug this in, we get delta GR is equal to 2 delta G, 2 delta G naught, which would take us somewhere all the way down here. And clearly that's not true. So therefore, this has to be false, and that's our final answer. Does that make sense? Yes? Scroll, I'm looking at your face. Yes, I'll redefine that. So delta GR, that's the Gibbs energy of the reaction. So that is defined. This is basically saying we have a bunch of bonds of A and a bunch of bonds of B, and we want to break those bonds and form new bonds to make C, right? We like, they want to form the more bond, like enthalpy favored reaction, or enthalpy favored bonding atomic arrangement, however you want to phrase it. And that's why it's a linear progression as you create more of the new bonds. It's just fully dependent on the number of new bonds, or the number of new product you've created, because it's based on the reaction. Delta GM is based on mixing. So this comes down like the Gibbs free energy of mixing. So this relates to the entropy that's being created. Because we're mixing, you can think of mixing this whole tub of you can think of it as literally just like ping pong balls of different colors, right? We want to have as many different colors as possible to increase that entropy, which is why it actually goes up and goes back to 0 as we get towards the complete reaction. So delta G is just the overall. It's the sum of those two, delta GR plus delta GM. It's the overall Gibbs free energy. And then this point right here is delta G naught, which is the Gibbs free energy for the overall reaction. And this point in the middle, minimum delta G is equal to equilibrium. Does that make more sense? Beautiful. Okay, I love the thumbs up. We're gonna move on. Alrighty, now we have another question. So Ellingham diagrams are a very big concept in this class, and Layli especially, she actually uses it in her work, and it describes a lot of the thermodynamics behind the kind of research that she does. So I think she does a good job of emphasizing its importance in her class. So they're a good concept to review and make sure you understand. So now we have a bunch of statements about what is, again, not correct. So let's just remember what an Ellingham diagram looks like. We have chow, things like this, and we have delta G. Delta G. My laptop also doesn't have like a functioning touchscreen in the middle of it, so whenever I try and write in here, it gets like all. Anyways, I'm just a bit of a disaster right now, but such is life. So we have delta G versus T as a graph, and then we have a bunch of lines on it, like chow, 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 wow. And these lines will say something like 2 mg plus O2 is equal to 2 MgO. And what this is saying is this is showing the Gibbs free energy for this oxidation reaction. So anywhere in a state above the line, then we're going to favor the forward reaction. So we're going to produce MgO. But anywhere below the line, then we're going to produce Mg. So if we're in a state like here, for example, then we're going to want to make Mg. And something that, so something that, for example, that's MgO, but then what if we had, for example, over in this line, and now we have Ti plus O2 forms TiO2, right? Now what's going to happen? So what we can think about is, again, anything above the line, we want to form the oxide, and anything below the line, we want to form the metal. So now we have these two things next to each other. What's going to happen? Remember, we want to decrease, we want to minimize the Gibbs free energy as much as possible, right? Yeah, overall. So what is oxygen going to do in this situation? Oxygen is going to go in the oxide that has the lower Gibbs free energy. So we're going to take all of the oxygen from TiO2 and we're going to go like, chow, we're going to use this and we're going to form MgO. So in this case, we would end up with MgO and regular titanium. And that's what you'd end up with. And that's kind of how you can think about these diagrams. There's also a lot of other intricacies to them about like the partial pressure of oxygen needed to make this happen, like the scales on the side and the slopes and all of that. But this is the overall, how do you read it? What are we looking at here? How do these reactions take place with each other? So now that we have that kind of basis, now we can go into the question. So let's start by just reading through the different options. So the first is that reactions closest to the top of the diagram are associated with more stable oxides. B is that they can be used to determine the partial pressure of oxygen. C shows that they have temperature dependence of stability of oxides. And then D says that closer to the bottom of the diagram are most unstable metals. So the reason I went through those so quick is before we start talking about anything is that we can immediately recognize A and B are complete opposites, right? So if we have stable oxides at the top, stable oxides, that means that we should have, wait a second. Yeah, if we have stable oxides at the top, we should have stable metals at the bottom, right? Because they're going to be flipped. I was hyphy to myself out there because whatever is stable at the top, the opposite's going to be stable at the bottom. But in this case, A is saying we have stable oxides at the top, but unstable metals at the bottom. So therefore, one of these has to be true versus false, right? One of these has to be the false answer. So inherently, we know that B and C must be correct, but let's prove it to ourselves now before we come back to A and C. The first one is that the Ellingham diagram can be used to determine the partial pressure of oxygen in equilibrium with the metal oxide at a given temperature. And this is one of the fancy intricacies that I kind of alluded to about the Ellingham diagram. So if you go to an Ellingham diagram, we have, delta G, and then we have T, we have all these lines, and then you also have these like fancy lines along the side, like all these scales, and it says over here like PPO2, and then you have like the little dots, and if there was a question about this, which I don't think there is, then I would go into more detail about how to read these, but I have not prepped for it. So I can talk about that afterwards if you want, but right now I won't. But essentially what you can do is like for some given partial pressure and temperature, you can form the little ka-chow, form a line between it and then measure off, the partial pressure of oxygen needed. Hopefully, Lily give a much better example than that. And I can, as mentioned, after the review session, I can go into more detail with like an actual Ellingham diagram in front of me. But that's something that you can do with it. So we know that this is true. And then for C, it shows the temperature dependence of the stability of oxides. And once again, we know that this is true because we're talking about oxides and their stability. We're talking about how oxides versus metals exist in relation to each other. That's talking about their stability. And one of the axes is temperature. So therefore, we're showing the temperature dependence of that. Next, let's get back to A and D. So now we're talking about where are things stable. And as mentioned, at the top, if we were to draw these, I drew MgO on the top and MgO on the bottom. And this shows that in general, at high Gibbs free energy, then we have an oxide on the top. So that means that stable oxides are stable near the top of the diagram, which means that A is true, and that must be that D is false. So D is our answer. Another way that you can kind of remember this, so as we go towards the top, that is increasing the Gibbs free energy, right? We typically want to decrease the Gibbs free energy. And a way that we can decrease the Gibbs free energy is by increasing the entropy, right? Is lower Gibbs free energy. And entropy relates to the disorder of the system, and big way that we talk about entropy is through molecules of gas that are present. Because if you think about gas, they're moving all over the place. They're like bumping into each other, right? They have really high energy. That's really high entropy. So high entropy is equal to high, like moles of gas and gas. And like numbers of gas, that would relate to having O2 as a gas, not within the oxide. So if we have O2 by itself, not within the oxide, that means that we have more gas, which means that we have more entropy, which means that we have lower delta G. So therefore, we have to have O2 down at the bottom, and then the oxide at the top. So that's a way that you can kind of think about these Elegant diagrams. If you get on the test and you can't remember exactly what it is, try and work your way backwards from the general concepts of where these diagrams are produced from, which is entropy and Gibbs free energy. Moving on to question 3. Do you want to record? Oh no, OneNote, what are you doing? Okay, give me a sec. OneNote is glitching out on me. Here we go. Okay, now we're on to some longer answer questions. Oh my gosh, Keith, do you want to come explain how reversible heat engines work? Yeah, this is the one where I literally got 0 out of 10 on the test. So as mentioned, like there's no issues with like getting 0 out of 10 on questions, but I personally do not want to explain this question because I did not understand it then. I don't understand it now. So Keith has gladly volunteered to do his little spiel on how to solve this.
That's right.
Yes. Yeah, that's what.
Okay, so the way I thought about this is it's a thermal heat engine pumping out heat from, they're saying it from a high energy to a low temperature reservoir. So there's a high, then there's a low temperature here. Then this is the engine. Performs work W and it rejects thermal energy into a low temperature reservoir, which consequently increases. The two reservoirs are initially at temperatures T1 and T2. Let's call this T1 and let's call this T2. And heat capacities C1 and C2 respectively. Assuming C1 and C2 do not change with temperature, calculates the final temperature of the system as a function of C1 and C2. So the first thing I'm going to do is like, first of all, the heat is taken from this into the engine. Then the engine dumps the heat into the low one. So once this loses heat, it's gonna drop in temperature from T1 to TF. Now we know work done in this case is just gonna be equal to Q, which is equal to, okay, let's not call it work for now. That's gonna come up later. But U is equals to C1 times the temperature change. This is gonna be T1 minus T5 TF. We don't need to go through the integrating process because we know this is a constant. So this is the work done to turn it from that. This is the work that's work in. Sorry for the weird spelling. Work into the engine. Now this is what we call a reversible heat engine whose efficiency we know is 1 minus T cold over T hot. So 1 minus T 2 over T1. This is the efficiency of the engine. And we know that efficiency is equals to work out over work in. So to find the engine also does work and puts the work into the low temperature. So the temperature goes from T2 to TF. Therefore, the work done in this is going to be Q is equals to C TF minus T1 minus T2, sorry. And this is C2, let me specify. Work out from this equation, we get work out is equals to efficiency times work in. So work out is gonna be this C2 TF minus T2 is equals to 1 minus T2 over T1 times C1 TF minus T2. Sorry.
Oh, it doesn't work in the middle of the screen. The touchscreen doesn't work in the middle of the screen. I scoot over to the side, yeah.
TF minus, what was it again? So the goal of the question is to find TF as a function of everything else. So first of all, it expand the brackets, then collect the terms and isolate for TF. So C2 TF minus C2 T2 is equals to, okay, 1 minus T2 over T1 times C1 TF minus C1 T2. Then open these brackets too. C1 TF minus C1 T2 plus C1 TF C1 T. Okay, this is a minus, so doing this times this, and then the 1 minus C1 TF times T2 over T1 plus C1 T2 times T2 over T1. So which terms have the CTF? It's gonna be, okay, let me just also write this here. The CTF terms is this, and this. So I'm gonna wanna collect them over on this side. So C2 TF minus C2, okay, plus C1 TF is equals to, there's also this, whose sign is positive. Let me move to the side here. So we just worked out TF. Is equals to C2. So this is the equation then. just simply divide. So divide it by everything else on this side. Then this should, we just use the principle like Carnot cycle, where engine efficiency work out working in terms of C1, C1, C2, T1, T2. But I just said look out because there's so many variables, I might have messed up something, but this should be the correct way of doing it. I'll hand it back to Sarah.
That was fascinating to pay attention to. I had no idea. Wow, thank you for explaining that. Yeah. Amazing. So now we're going to move on to things that once again I can explain and understand. So now we're talking about copper. Copper melts at a pretty high temperature and drops of being supercooled before isothermal solidification occurred. So what does this mean? Typically, you know, if you cross that temperature, then you turn into a solid. But for you know, we're able to cool it down without like adding any sort of nucleation site for solidification to occur. You can actually cool it down pretty far. I think you guys did that in 2A where you like super cooled water. Anyways, you don't actually need to know what that is, but it's kind of cool to think about. And now we need to calculate the enthalpy change, the entropy change, the entropy change of the system, and the entropy change of the surroundings, and then the total entropy change. And then we want to comment on the results, and we're given a bunch of these values. So this is where it just becomes a bit of, you know, a calculator kind of thing. So we know that delta H is equal. So we can start by drawing this. So we have, yeah, we're staying at 847 degrees C. But we have this value right here at 1083 degrees C. So we need to find a way to calculate the enthalpy change at this temperature when we're given the values for this temperature. So I'm going to start by drawing it out. So we have copper at 183 degrees C, and we're solid. Oh, and we're liquid. And then we go to 847 degrees C, and we're liquid. This is the supercooling process. And then we solidify to 847 degrees C as a solid. And we want to figure out what this is, right? What this, you know, what this changes, but we don't actually know. But what we can do is we can calculate, did we do this? Because we can use like the equation for delta H. Did I do this? Let's where Haiku is gonna yoink this process and then explain it. Yeah, and then we can go back up to, okay, yeah, so I did this a bit reverse. So this is the process that we know, but let's reverse it a little bit. So let's say we know that this is our starting material, is we have 847 degrees C, and we're at a liquid. This is where we start. Huh? And we want to get to, this is our goal, to get to 847 degrees C as a solid. So this is what we want, but we don't know what this process is. So we have to take a bit of a roundabout way. We can go up to 847, not 847, to the 1083 degrees C as a liquid. undergo the phase change to 1083 degrees C solid, and then cool it back off. So what we're going to do is we're going to go through this process, and it'll give us the exact same answer as if we went this way. So that's kind of the basis of what we're doing. And then we have our equations. Delta H is equal to the integral of Cp dt, and delta S is equal to the integral of Cp over T dt. So let's start by doing number one. I'm going to do it on the right side of my page here. So number one, we want to calculate the enthalpy change. So I'm going to write this out as one very long equation, and I'll say that the delta H for, liquid to solid is equal to the delta H, liquid to liquid at, like delta H. I'm going to call this 1, 2, 3. Delta H1 plus delta H2 plus delta H3. So delta H1, that is heating it up, right? So we're going to say it's the integral from the initial temperature, which is 847 degrees C, to 1083 degrees C, Cp dt, and this is Cp of the liquid, so I'm going to put a little L up there. And next, delta H2, that's the phase transformation. So that's going to be delta H of liquid to solid. So this is the delta H of the phase transformation. And now we're going to have, again, stage 3, which is where we cool it back off. So that's going to be the initial temperature, 8 degrees C to 847 degrees C of Cp, now solid, dt. So the next thing I'm going to do is I'm going to put in the equations for Cp, or I'm going to put in the values, and I'm also going to change these values here. I'm going to change them from Celsius to Kelvin. So 1083 degrees C is equal to 1083 plus 273, 1356 Kelvin, and then 847 degrees C is equal to 847 plus 273, 1120 Kelvin. Now, if you would write this out, we would get a very nice long equation of the integral from 1120 to 1356. Cp liquid is 31.35 dt plus negative 12,958 plus 1356 to 1120. Cp of a solid, 22.61 plus 6.27 times 10 to the negative 3t, all dt. So the key things to note to make sure we get correct here is making sure we convert to Kelvin, making sure that we have the right temperature bounds. So the bottom temperature bound, that's the initial T, and initial temperature, and this is the final T. And note that these are different for our first and our second, because the first one is when we're going from low to high, and the second one is when we're going from high to low. And then the other thing is make sure we get the right equations for Cp in there. In the sake of time, I'm not going to calculate this. I'm not going to integrate it. So I'm high-key just going to steal it from my solutions. Ciao. If you do have questions about the integration process, feel free to stick around after this and we can go over that. But that would be your final answer. Question 2 is now the entropy change of the system. So now we're going to do delta S, again, liquid to solid, is going to be, it's the exact same kind of setup, where it's delta S from the first process, plus delta S from the second process, plus delta S from the third process. So we have, again, from 1120 to 1356, we're going to have Cp of the liquid over T dt. And now we're going to have delta S of the phase change, and then we're going to have, now from 1356 to 1120, Cp solid dt. So we have equations for Cp. Cp over T dt. We have equations for Cp, but the real question here is, what is this value? What is the change in entropy? And this is where we remember that, well, you can approach this from a few different ways. You can just remember that delta S, for a phase change, right, delta S naught is equal to negative delta H naught over T. you know, that's something you can remember. If you can't exactly remember that, or if you're curious to where we get that from, or you forget, we remember that delta H is equal to delta H minus T delta S. So at equilibrium, which is when we have this phase change going on, delta G is going to be equal to 0. So now I can set delta H is equal to T delta S is equal to delta H over T. So that's kind of the derivation behind it. Yeah. And the temperature that we use there is that temperature at which the phase change takes place. So in this case, it's going to be the temperature of solidification, or the melting temperature, whatever you want to call it, which is 1356 Kelvin. So now we can kind of write this out, and now we have the integral from 1120 to 1356 of 31.35 over T dt plus, and now we have negative 12958 over 1356. So that's delta H, and that's the temperature at which it's occurring. And then we have 1356 to 1120, the integral of 22.61 over T plus 6.27 times 10 to the negative 3, all dt. So once again, you can calculate this. You can do the integral for the sake of time. I'm not going to go through that. You would get a value of this. So question 3, we're going to scoot you down a little bit. Question 3 asked us now the entropy change of the surroundings associated with this. So you're like, what? Shouldn't it be the same as the entropy of the system? But that's not necessarily the case. Because entropy, of course, depends on a lot of factors. What would be the same, though, is that we know that delta H of the system is going to be equal to delta H, or the negative delta H of the surroundings. And you can think of this in the sense of, the way that I like to think of it is that delta H is like the heat, right? And heat is never lost or gained. It's like you have some sort, it's always preserved. It's like mass, right? You're going to take a whole course on heat transfer next year. It'll be a good time. But you can think of it as like, oh, if you output heat, from a radiator, the system's going to feel that. Or let's say you yourself start doing work and you start like, I don't know. These are really poor examples, but heat is never lost. So delta H is like heat, so it's never going to be lost. It's going to be gained by the surroundings. But entropy has to do with the disorder, right? And that's always increasing. You can't take from one area and give it to another in exactly proportional amounts because entropy always has to increase. So that's not necessarily going to be the case. So the way that we calculate this, so we know that delta H of the system is going to be delta H of the surroundings. And this is going to be for the overall equation. We're not looking at a specific temperature anymore. Now we're looking at overall. We're not looking at the whole little, the little pathway that we came up with. So we know that delta H of the surroundings must be equal to 12,725 joules per mole, because that's the negative of what we got in part 1. Now remember that delta S, as we went through before, is equal to delta H over T. So to get delta S of the surroundings, we can plug this in. Now you're like, but Sarah, what temperature do we use? And again, this is overall. If you're looking at the actual reaction that's going on, it's isothermal, right? We're staying at the same temperature. It's isothermal solidification. So that means that we're going to be staying at the same temperature of 847 degrees C, or 1120 Kelvin. We're going to be staying at that temperature the entire time. So while we went through that whole little shenanigans to get the overall, delta H of the system, we don't need to do that for the surroundings. We can just take the overall reaction. So that would be 12,725 joules per mole divided by 1120 K, and you'll end up with, I don't want to plug that into my calculator, 11.36 joules per mole K as your final answer. And the last part of the question was the total entropy change for the system and the surroundings. So total entropy, you're just going to sum them up. Total entropy would be equal to 11.36 minus 9.365. So that's from the surroundings, which is number 3, and that's from the system, which was number 2. And you'll end up with a value of 1.995. And this just goes to show that once again, okay, as I mentioned, this is a positive value because entropy is always increasing in the system or in the overall, in the world, entropy is always increasing. So even if our actual reaction was decreasing entropy, when you account for the surroundings, then it's always increasing. And that is this question. Are there any questions before we move on? Taking that as a no. Beautiful. As a reminder for folks who are online, your yes. Yes. Yeah, so that represents the three different stages. So we have the first stage as we go from liquid and we heat up the liquid. Then we have the second stage as we go from liquid to solid, and the third stage as we cool down the solid. Because we don't know how to go directly from the liquid to the solid, we don't have any values to do that. Does that make sense? Yeah, so that is a great question. From a theoretical standpoint, so the question, if folks didn't hear it online, is why is this value from going ka-chow, 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 different than the value of that we got for 3 for the surroundings? So from a theoretical standpoint, we know that entropy is always increasing. So the entropy of the surroundings cannot be equal to the entropy of the system because then they cancel each other out and there'd be no change in entropy. But we know that it's always increasing. From a more mathematical perspective, what we can think about is that the entropy of the system, right, depends on the entropy of the system is due to the solidification. So we're going to be losing entropy, right? And it has to do with the actual molecules themselves and how they're reacting, which doesn't necessarily relate to the change in enthalpy that's going on, right? The entropy and the enthalpy, like they're kind of related, but like not really. They're different entities. So the entropy has to do with how they're arranged relative to each other. The entropy of the surroundings, however, has to do more with, I like to think of it in this case, as like, you're not really changing any of the particles in the surrounding, right? You're not like adding particles of gas or adding, like changing the bonding of the surroundings, which can change the entropy. What we're doing with the surroundings is we're changing the heat that's available, right? And if you are outputting heat, if it's exothermic, that's going to add heat, and heat relates to the kinetic energy. So if you add heat, molecules are going to start moving a lot faster. So that means that they're going to have more energy, and that increases their entropy because now we're moving around, there's a lot more disorder. And contrarily, if you have an endothermic reaction, then you are removing heat from the surroundings, and now they're going to be moving slower. That's going to decrease the entropy. But this heat doesn't have to do with the actual entropy of the reaction itself. This is more dependent on the enthalpy, which is where we get this equation from. Delta S is equal, or, again, delta S of the surroundings is equal to delta H of the system divided by T. Because what this is saying is now whatever this change in energy is, the change in enthalpy, right? That's the heat that we're either putting out to the surroundings or taking from the surroundings. That's going to change the entropy of the surroundings. Does that make sense? I'm glad. All righty. Question 5. Now we have a little fill in the blanks question. Bit of a breather after that beefy integral one. Assume that we are dealing with a single component system and that we only have PV work. How would you use Helmholtz energy to determine if a process is reversible or irreversible? Hint, to help you out, I provided a formula of the answer below. So the real trick to this question is remembering what is Helmholtz energy. Do we ever talk about Helmholtz energy? Not really. It's like briefly mentioned and then never brought up again because it's not used commonly. And that's why I'm searching through my notes to find it. What did I? Aha. I lied, I can't find it in my notes. It's here somewhere. Aha, so Helmholtz energy is given, let's remember, A is Helmholtz energy is equal to U minus TS, where U is the overall, energy of the system, and then we have T and S. But we can't actually measure the total energy, right? That's like a really difficult thing to quantify, which is why we use, delta H instead to Gibbs free energy. But Helmholtz energy is a quantity, and it's given by A, and this is why we should kind of consider it. And it is given at a constant volume and pressure. An irreversible process will lead to now it's basically the exact same as Gibbs free energy after that. It's treated the exact same way, it's just different variables that are at play. So an irreversible process will lead to a decrease of the Helmholtz energy, and it will be at its minimum at equilibrium. So this is the exact same as Gibbs free energy, right? So, Gibbs energy, we have delta G on the y-axis, and then we have, the number of moles of reaction that have gone on, and we have something that looks like this, you know, like X, whatever you want to call it. Then you have the whole like ka-chow, we were talking about that earlier. It's the exact same thing for this question, but instead of delta G, now we have delta A, and that's literally the entire difference between Helmholtz, in practicality, between Helmholtz free energy and Gibbs free energy. I'm just gonna make sure I didn't totally goof. Oh, it's temperature and volume. Oh, I goofed this up. Temperature and volume, not pressure. Yeah. So it's typically at a given, an irreversible process will occur at a constant temperature. And next, we're talking about Gibbs energy determined for processes reversible or irreversible. So, as mentioned, we're going to want So how to determine if a process is reversible or irreversible? High key, don't remember. We're going to check this. Oh, literally? Yeah, I should know this. We're going to copy this and then I'll explain it with words. Can you scoot over there, please? So we're going to be talking about a closed system again, but now we're going to have constant temperature and pressure instead of volume. And this is the big difference between Helmholtz free energy and Gibbs free energy. And now an irreversible process will decrease Gibbs free energy, but at equilibrium, then G will be stable. And okay, so the way that we can think about this, and this is why we have constant temperature actually, is because we're only doing pressure volume work, right? And this is a kind of work that typically, if we're dealing with a reversible process, if we're like at a constant temperature, we're changing the pressure, then if we're words. For a given process, right, if we're keeping it at a constant temperature, now we just have any change in Gibbs, or let's deal with Gibbs free energy. Delta G is equal to delta H minus T delta S. So we're going to say that we're at a constant temperature. So that's not going to be changing, right? This temperature is constant. And if we're doing an irreversible process, we're keeping this constant. All we're changing is pressure and volume. We're not adding anything to the reaction. We're just like kind of moving around the physical environment around it. By changing that physical environment, typically, think like the pressure, the material will like accommodate for that change and it will be reversible, but constant. It's constant Gibbs free energy. So delta G is equal to 0. But it's irreversible if it's not. I'm sorry, brain stopped working. Don't have a better explanation than that right now. Okie dokie. So next we have 1 mole of oxygen is mixed with 3 moles of nitrogen. Assuming that the gases are ideal, what are the enthalpy, entropy, and Gibbs energy of mixing at 500 K for 1 mole of the mixture? So, the way that we approach this, so we're dealing with ideal gases here. So that's the big thing that we need to talk about. So we have ideal gas, we know PV is equal to nRT, right? Oh, literally so true. I should know this. So we also know that they're ideal gases. So let's start by breaking this down. So delta H, right? Let's remember what delta H relates to. So delta H again relates we're having kind of bonds that are forming or any sort of heat, any sort of interaction between the different particles. But one of the properties of an ideal gas is that the gas molecules do not interact. Molecules do not interact. Therefore, there's not going to be any sort of bonding that's changing or bond energies that are going on, no sort of heat that's being released. So delta H mix is going to be equal to 0. And the next thing that we can talk about is entropy, delta S. And this is not going to be 0 because we have, as mentioned, then, entropy is the disorder of the system, and we're adding a lot of moles of gas. So they're going to be all disordered here. And now that we're mixing them together, it's going to add to the disorder, and it's just so chaotic. And the way that we calculate this is equal to the negative sum of xi ln xi. Let me just make sure I didn't goof that. Okay. Negative r of xi ln xi. Yeah. So r is the gas constant, and this is basically what gives us our units for this, and then xi ln xi, x is the molar fraction within the mixture. So let's figure out what that is. So we have oxygen. So we have 1 mole oxygen. We have 3 mole of N2. So we have 4 mole total. So x of O2 is equal to 1 mole over 4 mole, which is equal to 0.25, and x of N2 is equal to 3 mole over 4 mole, which is equal to 0.75. So now we just have to do negative r, and now we do the sum of both of these. So we're going to start with oxygen, 0.25 ln 0.25 plus 0.75 ln 0.75. And remember, r is equal to negative 8, or it's 8.314 joules per mole, I believe it is. It has to be joules per mole K. Yeah, joules per mole K. So we're going to end up, if you do all of this, you get a value of 4.675 joules per mole K as your answer. And now we want to calculate the Gibbs energy. So this is where we go back to our classic equation. Delta G is equal to delta H minus T delta. Of course, these are all mixing. But we know delta H is equal to 0. So now we can just say it's equal to negative T delta S mix. And this is where we just plug in the values, 500 Kelvin times 4.675 joules per mole K. And if you were to do this, you get a value of negative 2337.5 joules per joules. It's not per mole. That was a mistake on my part. The reason it's not per mole is because we actually included, we accounted for the moles when we're doing all of this. Like we have the 0.25 and the 0.75, so it's going to be joules per K. So we end up with negative 2337.5 joules. Yeah. Any questions about that? I'm not hearing any, so we're going to move on. Question 7, now these are just discussion questions. So the first one is, why do most of the lines on the Ellingham diagram have a positive slope? So this goes back to the definition of the Ellingham diagram to begin with. So if we remember, the Ellingham diagram, was delta G versus T. So what we're plotting here, delta G is equal to plus delta H minus T delta S, but we can put this, if this is our Y variable, and T is our X variable, we can put this into Y equals MX plus B, where delta G is Y is equal to B plus, X times M. So it's Y equals MX plus B, but a little bit arranged. And what this shows is that the slope is equal to the negative of delta S. So you'd be like, oh, but it's got to be, it has to be a negative value, then why is it positive? We know that delta S is going to be negative for this reaction because remember, we're turning from a metal plus O2 to some sort of oxide, and that's going to decrease the entropy. So the change in entropy for this reaction will be negative, which means that we'll end up with a negative of a negative, which gives us a positive slope. Positive slope. However, now we have this one line, 2C plus O2 is equal to 2CO, and this has a negative slope. So what this means, again, the slope is equal to negative delta S. So to have a negative slope, then what that means is that we have an overall, like delta S has to be bigger than 0. Why is that happening? We can look at the moles of gas here. So we're going to have solid, or I guess 2 moles solid, and then 1 mole gas. But now our product is 2 mole gas. So what we're doing is we're increasing from 1 mole gas to 2 mole gas, and that's going to increase the entropy of the system because now we have a lot more disorder, right? So delta S increase with increase mole gas, therefore slope positive. And now we have, how would you describe the line of the slope for C plus O2 is CO2? So we're going to do the exact same thought here. So we start with 1 mole solid, 1 mole gas, but now we end up with 1 mole gas. So now we have the same number of moles of gas on either side of the equation, same number of N of gas. So that means that we're going to have roughly a horizontal line. Does that make sense? Scarlett, you okay back there? Beautiful. Love the thumbs up. Guys, we're almost done. Okay, question 8. We need to purchase an oxygen tank, which will be stored at a pressure and a temperature and a diameter and a height, and we're filling it up we don't want to fill it up with a lot of gas because, you know, we're a little cheap. We don't want to fill it up with too much gas because that's pricey. So we're asking if we prefer the gas behaves ideally or as a van der Waals fluid. So essentially what this is saying is we're given all of these values, which I'm going to write out here. P is equal to 200 atm. T is equal to 300 Kelvin. Diameter is equal to 0.2 meters. Height is equal to 2 meters. And then we want to know if we'd rather behave ideally or as a van der Waals fluid. And we want to minimize N. So we're going to start by talking about an ideal gas. Ideal gas, because these are easiest. PV is equal to nRT. And we can solve for N is equal to PV over RT. And now we're having a cylinder, so we know that the volume is equal to pi r squared times h. So I'll say r is equal to 0.1 meters. So now we can plug all these in and say P times pi r squared h all over, you know, the gas constant times T. And if you plug those values in, you know, I'm too lazy to calculate it. The trick here, so we're going to end up, let's say, 510 moles. The trick here is to make sure that your units work out. Use unit analysis. So what I mean by using unit analysis is, let's say we put this over to the side and we're going to end up with like atmospheres times meters squared times meters, because that's P r squared h, all divided by Kelvin, and then the gas constant. So if you use 8.314, the units for that are joules per mole K, or like joules per K or whatever, right? And that's not going to cancel out your units. So you have to make sure that you use the right unit conversions, the right unit analysis here, so that you cancel it with the atmospheres, because otherwise you'll end up with not a great answer. The other option is to convert atmospheres into SI units, so convert it into pascals, and then that'll cancel it with joules, but that seems a bit more complicated, because I think you should be given a formula sheet with the different gas constants. Anyways, the next stage is dealing with our van der Waals fluid. So fun fact, I've literally never thought about van der Waals fluids since writing this exam. Maybe in 2D, but that's about it. So you don't need to worry about it too much for after this. I think it was on test 2. Literally could not tell you where those equations even are on my formula sheet. So we're going to go back because there are equations. So you will be either given these equations. We might have been given them at the top, honestly, now that I'm thinking about it. At the bottom. You will be given this equation. If you aren't, then that's kind of not cool of Laylee. Keep in mind, we had an open book exam, so we didn't need to memorize anything. It was just all given to us. But we have, oh God, we have this lovely equation for van der Waals fluid. Ciao. Oh no, one note, don't die on me. Don't die on me. Yeah. Okay, one note is dying on me. Just give me a sec. Here we go. Hooray. So we know van der Waals fluid. Now we have, instead of having that lovely little ideal gas equation, now we have P plus N squared A over V squared times V minus NB is equal to nRT. So we can look at this and we're like, okay, we have values for A and for B. We know P, we know V, we know V, we know R, we know T. Now we just need to solve for N. Easy. So there's two ways you can do this. So if you look back at my solutions, I expanded this term out to try and solve for N. That seems like do you guys know how to use the solve function on your calculator? The solve function? Yeah. I'll go through it quickly because I'm seeing one person who doesn't know exactly. So you can type in whatever equation you want and your calculator can give you the answer to it. It uses, I think, the Newton-Raphson method. You learn how this works in numerical methods in third year. It's actually pretty cool. But let's actually practice typing this in. Haha. So we know that the pressure is going to be 200 atmospheres plus, and then n squared. So I'm going to put this as x squared because that's going to be our variable times 1.36 because that's A all over V squared, which is, what was our volume? Oh, we had to calculate our volume. That's such a pain. Our volume, I'm going to calculate that now. Pi times 0.1 squared times 2 is equal to 0.06283 meters cubed, which is equal to 62.8 liters. So we're going to put in 62.8 liters all times 62.8 liters. I don't need the units here. 62.8 liters minus x times our b value was 0.0318. And this is all equal to x times, oh frick, what's our r value? I never remember what r is if it's not 8.314. 0.08206. 0.08206, 0.08206 times the temperature, which is 300K. So what we're going to do on our calculators is we're actually going to plug in this full equation. So what you're going to do is you're going to start typing it in as per usual. So I'm going to do bracket 200 plus, and now I get to x squared. And you might be like, Sarah, how the heck do I type in x squared? And this is where we're going to use the fun yellow and red writing on our calculator. So on the top left of your corner of your calculator, if you have, the standard Casio FX McMaster calculator, you can hit alpha. And now we're going to be, because alpha is in a little red, a little pinkish. And now what we're doing, if we hit alpha, now we're accessing all the buttons that are written in red. So the end parentheses button, that guy, above it in red is written X. So if we hit alpha, then we hit that button. Now we get X in our equation. And you can type in X, and I'm going to type X squared times 1.36 divided by 62.8. And I'm just going to keep typing in this equation, 62.8 minus, again, alpha X times 0.0318 end bracket. And now I get to this equal sign. You might be like, Sarah, now how do I do the equal sign? Again, if you hit alpha and then right below the alpha and shift buttons is a button that says calc in white and above it is an equal sign in red. We're going to hit that times 0.08206 times 300. So now I've actually typed the whole thing in. Now you hit shift, which is yellow, and then solve, which again, which is that yellow calc button that also has the equal sign. Now it asks you for a guess of x. This actually just helps with the numerical methods process, but you just want to give it a guess. So here it's asking us to figure out the number of moles. So we know it's going to be somewhere close to that. So I'm going to put in 500 as my guess. I'm going to type in 500 equals, and it's like, x equal to 500. I'm like, yeah. Then I hit shift, solve again. Syntax error. What do you mean syntax error? Oh, you hacker. Okay, my bad. I typed it in wrong. Um, Give me a sec. X. times 0.0826 times 300. Just solve. So now I'm going to end up with a value of, we'll see if this actually matches what I got last year. Because last year when I solved it, I got 564.94. I think I actually just killed my calculator. Ooh, golly, I did kill my calculator. I typed it in wrong. But if you solve this properly, you should get a value of 564. Ooh, yeah, we're not going to look at that. Theoretically, it should work. That's what I did to solve this equation. We look at 564.94 moles. That was a failed experiment, but alas, such is life. So anyways, oh gosh, the computer's okay. So we get this value of 564 moles. So now we're like, okay, we can either have 510 moles or 564 moles. Remember, we're cheap. We don't want to buy a big oxygen tank. We want to fill it up with the least amount of moles of gas. So we want it to behave as an ideal gas. And that would be your final answer. Does that make sense, other than the calculator thing being a hecker? Beautiful. Now on to question 9. When SO3 is decomposed at a constant pressure and some temperature, the partial pressure at the equilibrium gas is 0.05 atmospheres. What is this pressure? And then if it's increased to 1 atmosphere, how does the gas pressure change? So, we know that P, is this an undiagnosed? Oh yeah, oh golly, I hate these questions. So the way we do this is that we know that there's some sort of equilibrium at play, right? Because we have this equal sign here, we know that it's going to be going back and forth. And now, and we want to figure out, yeah, so we want to figure out what this equilibrium exactly is and what the other things are at. So we're going to create, it takes me back to grade 12 chemistry whenever I do these things, but we're going to do a little ice table. So we have SO3, 0.502, SO2. So what we're doing here is we're going to write out the initial, the change, and then the equilibrium. And we are talking about the moles here. Yeah, we're going to talk about moles here. So we're given a bunch of values in pressures, but we're actually going to be talking about the moles when we're talking about this equation, because the pressure before is not necessarily equal to the pressure afterwards, right? Because we're changing the number of moles of gas that are present. But what we do know is that the number of moles will be changing at some defined ratio. So we're going to do this calculation for each, or like per mole SO3. So we're going to start with 1 mole SO3, and we have nothing else. And the reason we know this is that we have SO3 is being decomposed. So we assume that we're starting with full SO3, and we don't have anything else that's present at the start. And what's going to be happening is that as we decompose this SO3, we're going to be losing some SO3. I'm going to call that X minus X. But we're going to be gaining O2 and SO2. And this is where we need to think about our mole ratio. So we have 1 mole SO3, 0.5 moles O2, and then 1 SO2. So for every mole of SO3 that we lose, we're going to gain 1 mole of SO2. So I'm going to say plus X and gain 1/2 moles, 0.5X of O2. Now we end up in equilibrium. We don't know what SO3 is. We know that whatever SO2 is, again, mole ratio is going to be 2 times whatever we have for O2. So that would be, but for now, we're going to leave this as 1 minus X, 0.5X, and X. Because now we know that the equilibrium is going to be the initial, I'll change that to a proper I, minus whatever the change is. So we're given these values and we're like, okay, so now we have our ice table set up. We kind of understand the situation. How do we actually calculate this, right? Well, we know that the partial pressure of O2 at equilibrium, so PO2 equilibrium, is equal to 0.05 atmospheres. And we know oh god, yeah. but we don't know what we can do from there. A fun little thingamajigger that we can do from this equation or from this ice table. So given, just in general, given AA plus BB is equal to CC plus DD, whereas lowercase is equal to the number of moles and uppercase is equal to some sort of element, we know that we can form the reaction constant is equal to the partial pressure of partial pressure of C, big C, to the power of small c, times the partial pressure of big D to the power of small d, all over the partial pressure of big A to the small a, times the partial pressure of big B to the small b. And basically what this is saying is that we have some sort of ratio between the partial pressures of the reactants and the partial pressure of the products. And this is always going to be constant, right? So as we gain a bit more of this, we're going to lose a bit more of that, and it's going to go back and forth, and these partial pressures are going to reach some sort of equilibrium. Whenever we're at equilibrium, we're going to have the same number. No matter how many moles, for example, you add more moles of A, that's going to change their partial pressures in order to maintain the same ratio. So this is at equilibrium. So let's calculate that for our situation. Yeah. So we know that Kp, again, Kp in this situation is going to be the partial pressure of the product, so partial pressure of O2 times the number of moles. So that's going to be to the 0.5 times the partial pressure of SO2, and that's to the 1. So I'm just going to leave that out because I don't want to include that, all over the partial pressure of SO3. So we're going to have this, and we're like, okay, so we know the partial pressure of PO2. How does that actually help us too much? And what we're going to do here is what we can say is we're like, okay, we actually know what this is. Let's figure out what PSO2 and PSO3 are in relation to, yeah. Instead of doing the partial pressure, we can also say that this is equal to the molar fractions, right? So let's make a new addition to our ice table called X. And what this is going to be is this is going to be X. We're just jumping around a little bit here. X is equal to the molar fraction of each element. So that's going to be, so the number of moles, mole at equilibrium, which is what we have listed in E, divided by the total number of moles at equilibrium. So our total number of moles, total N, is going to be equal to 1 minus X plus 0.5X plus X. And I'm just summing all of these values together. So if we add those all together, you get 1 minus 1 plus 0.5x, because you end up with 1.5x and then you minus x. So you have 1 plus 0.5x. So we can now plug this into x, which is 1 minus x over 1 plus 0.5x. And this is 0.5x over 1 plus 0.5x. And then x over 1 plus 0.5x. So now we know what these changes are, and we can use these to sub into the Kp equation. So we're like, okay, so we're getting closer to solving the Kp equation, right? Because Kp is really going to help us out here. Another thing, this equation, what we're gonna end up doing, so let's actually do that now. What we're gonna do is, again, we know what PO2 is, so let's sub this in. Let's try and solve for Kp. We're gonna have 0.05 atmospheres to the 1/2 times the partial pressure of SO2. And you might be like, Sarah, I don't know what that is, but remember the partial pressure is proportional to the molar fraction, right? So Pi is proportional to Xi. So what we can do is we can actually sub in our molar fraction instead of our partial pressure here, and that's what we just calculated down here. So I'm just going to sub those values in. So SO2 is X over 1 plus 0.5X. And now we have SO3, which is 1 minus X over 1 plus 0.5X. So now we have this equation, and now we only have two variables left. We have X and we have Kp. So we're working backwards with some knowledge that we know. We're like, okay, we just need to get one more of these variables, then we can solve the equation. And this is where we go back to, okay, what does Kp actually mean? Kp is the equilibrium constant. And the equilibrium constant is also, it's used for this relation, but it's also really handy to, again, go back to our Gibbs free energy. Our Gibbs energy is equal to negative RT ln of Kp. So we can actually do in this situation, we know our delta G, we were given that at the beginning. This is another strategy you can do, is gonna be like, what information were we given? So you know it's equal to negative RT ln Kp, which is equal to negative 94600 minus 89.37 T. So what we can do is we can rearrange this equation and solve for Kp. So Kp is equal to the exponent of negative delta G over RT, which is equal to the exponent of negative 94600 minus 89.37, and then the temperature here is 1000 Kelvin, all over 8.314 times 1000. And then if you do this, you get a value of 0.5331. So now we have our Kp value. We're going to take this and sub it in here. And what you can do, again, using your calculator, or you can, rearrange it if you want to be extra. I don't feel like doing that. You will solve this. No, actually, we'll rearrange it. I feel like that's a beneficial thing to go through. Oh God, OneNote, what are you doing now? OneNote, stay with me. Okay. So now we have a value for Kp. So now we have 0.5331 is equal to 0.05 squared times x over 1 plus 0.5x, all over 1 minus x over 1 plus 0.5x. So if we go to solve this, we can cancel out these denominators and bring the 1 minus x across. So now we have 0.5331 times 1 minus x is equal to 0.05 squared times x. Now you can rearrange and solve, but I'm too lazy to do. You will get x is equal to 0. What did I say? 5331? Oh, I was way off. That was Kp. 0.7045. Wow, OneNote does not like me right now. 7045. You might be like, Sarah, why do we even get x? What does this matter? And the reason it matters is because we want to calculate P total, remember? P total, and what this is going to be is equal to P SO3 plus, or the partial pressure, plus the partial pressure of SO2 plus the partial pressure of O2. And remember these partial pressures, or alternatively, that seems like a lot of work. Oh golly, OneNote, don't hate me. Don't hate me. OneNote will actually destroy me some one of these days. Go down, thank you, thank you. We also know that the partial pressure, so Pi, partial pressure of I is equal to Xi times P total. Oh God, it really doesn't like me right now. So now we know, we want to find P total, that's what we're trying to find. We know the X value and we know Pi of O2. So what we can do is let's calculate X for O2. Remember, we already figured out this equation from the ICE table is 0.5x divided by 1 plus 0.5x. Now that we know x, we can sub that in. 0.5 times 0.7045, 1 plus 0.5 times 0.7045. And if you calculate this, I'm too scared to change tabs again for OneNote glitching out on me. 1 plus 0. We'll get a value of 0.26 approximately. So now we can say that the total pressure is equal to the partial pressure of O2 divided by the molar fraction of O2, which is 0.05 atmospheres divided by 0.26, which is equal to, let me get the right answer. Did I goof this? So I 100% calculated something wrong. OneNote, come back to me. OneNote. Guys, what if OneNote just dies forever? Oh no, I just literally typed this into my calculator wrong. You would get a value of 0.19 atmospheres as your final answer. It was giving me a value of like 1 atmosphere, and I was like, I don't think that's right. So that's kind of a bit of a pain, but to kind of summarize what we did is we need to make an ice table to better understand the situation, and we add a little extra row to the ice table of X to talk about the molar fraction when it's in equilibrium. Next, we need to really rely on the concept of the equilibrium constant, so we can calculate it using the delta G values provided, and use the relation to the partial pressure and the overall molar fraction in order to figure out what that X value is at equilibrium, and then use our relation between the total pressure and the partial pressure to get the total pressure. Next, it said if the pressure of the equilibrium gas is increased to 1 atmosphere, what value should the temperature be decreased to produce a gas with a given partial pressure? So I'm just going to put this on the side. Now we know P total is equal to 0.05, is equal to 1 atmospheres, but we still want to keep PO2 is equal to 0.05 atmospheres. So the first thing that I think of is, okay, we know that XO2 is equal to PO2 divided by P total. So we can do that first of all and calculate what our X value should be, which would be 0.05 divided by 1. So now we want our XO2 to be 0.05. So we're basically just going to do the exact same process and work backwards here. We know that our XO2 is equal to 0.5x over 1 plus 0.5x. Now I can use this to solve what x is. So if we have 0.05 is equal to 0.5x over 1 plus 0.5x, we can solve that to get x is equal to. Is it going to crash out on me if I check the solutions? That's the real question. 0.1053. Oh, it works so fine. 0.1053. So now we have this x value. We can go back to our Kp equation. Kp, remember Kp is equal to PO2 to the 0.5 times PSO3 all over PSO2 all over PSO3, which is equal to PO2 to the 0.5 times XSO2 all over XSO3, which was equal to some equations with relating to X, PO2 to the 0.5 times X over 1 minus X. So we can take this X value we just calculated and plug it in here. So we're doing the exact same steps we did before, but now backwards. We can get Kp is equal to 0.05 to the 1/2 times 0.1053, all divided by 1 minus 0.1053. And if you were to do this, you would get a value of, I'm too scared to choose tab, 0.053. I'm gonna check anyways because I'm scared. Yeah, 0.0263. Is by 263. And now the last step, again, we know that Kp, or delta G, is equal to negative RT ln Kp, and which is equal to some number that we already calculated, or you could calculate that was provided. So now you can just solve and say T is equal to negative delta G over R ln Kp. We know what delta G is, or you can calculate it. We know what R is. We know what Kp is. If you sub all of these values in, you will get a value of 791 Kelvin. And that would be your final answer. So this is a bit of a doozy of a question, but it was worth 20 marks. So it's expected to take a long time. And really, it's all about making sure that you're comfortable with these concepts of the equilibrium constant, delta G with relation to the equilibrium constant, and using ice tables. Are there any questions? Go for it. So the question is, in the initial ice table, why did I put 1, or how do I know that 1 is the initial value for SO3? I don't. It never specified, so you can just make it 1 to make your life easier. So you can either say that, or you could give your final Because all we're talking about here is relationships between the different values, right? So I could make it whatever I want and it'll just be a larger volume than, if we just had 1 mole. But we're never actually giving any values as a specific quantity, right? It's all relationships to each other and molar fractions. So it's just easiest if we put it all with respect to 1 mole. Does that make sense? Exactly. It would just be like, instead of divided by 1 plus 0.5x, this would be like, if I made it like 10, for example, this would be 10 minus x. So now it'd be like, the final answer would be 10 plus 0.5x, 10, and there would just be different values associated like that. But you get the exact same solution at the end and just be making your life a little bit more difficult. Okie dokie. So our last question was electrochemical fuel cells. I won't lie, like I feel like cells, like you learn it in grade 12 chemistry, and I'm like, I know how these work. And then I got to this class, and you do it in first year chemistry, and I'm like, I know how these work. And I got to this class, and I was like, I don't understand anything. So if you feel that way, just know that same. Anyways, we're given these reactions, anode, cathode, and then we're given some overall reaction, and we know basically the properties of a bunch of these things, and then it wants us to calculate the voltage of an ideal fuel cell. So, similar to, I forget what van der Waals fluids, I literally have not thought about this since I wrote the exam. So I will be relying on my solutions to solve this because sometimes that's how life goes. And I don't have time to prep. Instead of switching back and forth, I'm just going to take a screenshot and then just scoot over to the side. So the first thing that we're going to do is we are dealing with an overall reaction that produces 2 moles of A2B. I don't like that. We want to do this per mole, right? All of these values are per mole. So I'm actually going to start by dividing this by 2. And we're going to get A2 plus 1/2 B2 gives us A2B. And one of the reasons we do this, okay, high key. I'm going to check my notes real quick because I don't have any idea what I did here. Okay, here we go. I'm going to divide these also by 2. So that's going to give A2 plus 2A2 plus 4E. And now we're going to have divided by 2 gives us 2A2 plus 1/2 B2 plus 4E. 4 electrons gives us A2B. And again, I'm doing this because we're making 1 mole of product, and the question is telling us per mole of A2B product. So I'm just making it in a line with that. And when I do this, what I can see is that we're transferring 4 electrons in this equation. So therefore, our variable Z is going to be equal to 4. And you might be like, Sarah, what is Z? Where am I going to be using Z? Great question. We're going to get there. So what we're going to do here is we're going to think about the different ways that we can solve this. So I'm going to we know that we are at a constant temperature is equal to 298 Kelvin and a constant pressure is equal to 1 atmosphere. We know that we've released 300 kilojoules of heat, so that is going to be equal to delta H is equal to negative 300 kilojoules, negative because it's releasing this heat. And now we want to figure out what delta S is. And again, I'm just going through this and trying to go through all of this. So we're given all of these values. So if we want to find the overall entropy change, we can say delta S for the reaction is equal to delta S for the products minus delta S for the reactants. Yeah. So the products are going to be, again, A2B. So that's going to be delta S A2B minus delta S A2 plus 1/2 delta S B2. Note that I did have to add a factor of 1/2 here because of our equation. We have 1/2 moles of B2, and these values are per mole. So we're going to end up with a value of 150 joules per mole K. And this would be multiplied by 1 mole if we want to be technical here, and it'll be minus 200. I actually hate my laptop with a passion, guys. Minus 200 joules per mole K times 1 mole plus 1/2 mole times 400 joule per mole K. And if you were to calculate all of this, you would get a value of negative 250 joule. I'm just going to put this as joule, per mole K. And I'm putting this per mole because this is assuming we're just doing a per mole of product. So now we have delta H and we have delta S. The next, just logical thing, if you're kind of fluffing around like me, I'm trying not to check the solutions. I'm like, okay, we're given delta H. We can calculate delta S. We know the temperature. Might as well figure out what the Gibbs free energy is, right? That's a thing we use in this course. So you know delta G is equal to delta H minus T delta S. So we can just sub in our values. 300 times 10 to the 3 joules per mole minus 298 Kelvin times negative 250 joules per mole K. Note that I was pretty lazy earlier on, but right now I'm using units within my calculations, and that's to make sure that my units check out. So we were given this value in kilojoules, but I converted it to joules because this is all in joules. This is just something that you should pay attention to, because if you don't, then you might be a little out of luck. So now with a value of 225,500 joules per mole. So now we're like, okay, we have delta G. What do we do with that? And this is where we use the equation. Delta G is equal to ZF fancy E. And this is like, what even is this? What are these variables? So Z, we already said that's the number of electrons that are being transferred. That's equal to 4. F is just a constant. It's Faraday's constant. It's, 96,487 coulombs. And then this fancy E, if you remember back to 103, everyone's favorite course, that's the electromagnetic force, EMF, which is equal to the voltage. So we can actually just use this equation and rearrange to solve. Epsilon is equal to delta G over ZF, and now it's just a simple plug and chug. 500 joules per mole, all divided by 96487 C times 4. And if you calculate this, you would get a value of 0.5843. Where did the negative come from? Oh, I forgot a negative sign. There should be a negative there. Yeah. 0.5843. And your units here, joules per mole times coulomb, this is just equal to 0.5843. Joules per coulomb is equal to a volt. Fun fact. 43 volts per mole. And that would be your final answer. And that is the end of this exam. Oh, jeepers. That was a fun remembering how to do this course. Thank you for bearing with me. I'm going to go to Teams. Ciao. And I'm going to stop recording, stop sharing my screen. Stop recording. Beautiful. And we're going to leave